to explore new paths for enhancing the performance of magnesium alloy materials. The research team adopted an innovative method combining masterbatch feeding technology with ultrasonic-assisted stirring casting to meticulously prepare a series of magnesium alloy magnesium-based nanocomposites with different contents of silicon carbide nanoparticles. During this process, the team strictly controlled the experimental conditions to ensure the accuracy and repeatability of each step of the operation, and was committed to laying a solid foundation for subsequent in-depth exploration. The core objective of this research is to deeply explore the influence of the feeding mode of nanoparticles and the enhanced weight fraction on the microstructure and mechanical properties of magnesium alloy or silicon carbide composites. The masterbatch feeding method shows unique advantages and can promote the relatively uniform dispersion state of silicon carbide nanoparticles in the primary MD phase. In sharp contrast, the original feeding method is highly likely to cause obvious agglomeration of particles, seriously affecting the uniformity of the internal structure of the material. With the gradual increase of the weight fraction of silicon carbide nanoparticles, significant changes occurred in the microstructure of the material. The primary MG grains gradually refined, and the MgAl intermetallic compound phase also became smaller. These changes in microstructure had a profound impact on the macroscopic properties of the material. From the perspective of mechanical properties, the hardness and tensile properties of magnesium alloy or silicon carbide composites show a significant improvement trend with the increase of silicon carbide content. When 2.0 Wt silicon carbide was added, the hardness of the material achieved the maximum increase, reaching 41%, fully demonstrating the reinforcing effect of silicon carbide nanoparticles. However, when the content of silicon carbide exceeds 2.0 Wt, the number of pores in the microstructure of the material increases, and at the same time, the phenomenon of particle agglomeration intensifies, which directly leads to a downward trend in the ultimate tensile strength and elongation. Among numerous experimental samples, the magnesium alloy 1,5-Wt silicon carbide composite material performed particularly outstandingly, demonstrating excellent tensile properties. Its yield strength was 151 megapascals, ultimate tensile strength was 192 megapascals, and elongation was 4.54%, which was an optimization of the performance of magnesium alloy materials in practical engineering applications.